Hi, Siddharth this side. So today we are here to discuss the topic, the dining philosopher problem in operating system. So firstly, we will see the list of contents what we will cover in this video. Firstly, introduction about the problem statement, understanding the problem with the code, the solution for the problem, and then conclusion. So firstly, introduction. The dining philosopher's problem is a classic synchronization problem. It is used to evaluate situations where there is a need of allocating multiple resources to multiple processes. Now, what is dining philosopher problem? It demonstrates a large class of concurrency control problems. It was designed to illustrate challenges of avoiding deadlock. And it was originally formulated by Edgar Dijkstra in 1965. Later, Tony Hoare gave the problem its present formulation. Now, need, what is the need of this problem? It is simple representation of need to allocate several resources among several processes. It represents a deadlock-free system and it ensures a starvation-free structure. Now, we will see the problem statement. So, as you can see here, consider five philosophers who spend their life thinking and eating. In the diagram, you can also see. And the philosophers share a circular table surrounded by five chairs, each belonging to one philosopher. And in the center of the table is a bowl of rice, and the table is laid with five single chopsticks. Now, when a philosopher thinks, he does not interact with her colleagues. From time to time, a philosopher gets hungry. He tries to pick up the two chopsticks that are closest to him, that is, the chopsticks that are between him and his left and right neighbors. Now, i- the next part of statements are a philosopher may pick up only one chopstick at a time. He cannot pick a chopstick that is already in the hand of a neighbor. And when a hungry philosopher has both his chopstick at the same time, he eats without glazing his chopsticks. And when he finished eating, he puts down both of his chopsticks and start thinking again. Now we will see or we understand the problem with the help of code. So as you can see here, let's use a given figure as a reference to understand the problem exactly. Yeah, so you can see the figure here that the five philosophers are represented by P0, P1, P2, P3, and P4, and five chopsticks, which are C0, C1, C2, C3, and C4. Yeah, as you can see here, code void philosopher while of 1 take chopstick of I, takes chopstick of I plus 1 modulo 5, eat, put chopstick of I, put chopstick of I plus 1 modulo 5, thank you. So, to understand this code, we first see that as you can see here, suppose philosopher P0 wants to eat, he will you enter into the function, philosopher function, and execute takes chopstick I. By doing this, it holds C0 chopstick. After that, it executes take chopstick I plus 1 modulo 5. By this, it holds C1 chopstick as since I is equal to 0, therefore 0 plus 1 modulo 5, which is equals to 1. So, similarly, suppose now philosopher 1 wants to eat, it will enter into the philosopher function and execute chopstick of I. By doing this, it holds C1 chopstick. After that, it executes the chopstick I plus 1 modulo 5. By doing this, it holds C2 chopstick since I is equal to 1 as 1 plus 1 modulo 5 is equal to 5. But practically, chopstick C1 is not available as it has already been taken by the philosopher P0 as the above code generates problem and produces rates condition. Yeah. So solution for this problem, we use semaphores to represent the chopstick, and this slowly act as a solution of dining philosopher problem. Wait and signal operation will be used for the solution of dining philosopher problem. For picking a chopstick, wait operation can be executed, while for releasing a chopstick, semaphore operation can be executed. So firstly, we will discuss about the semaphores. A semaphore S is an integer variable that apart from initialization is accessed by is two standard operation only, which is wait and signal. As you can see here below, the definitions of wait and signal. As for wait, while of s is lesser than equal to 0 and s we decrement the s. Now, next is definition of signal. So in signal, we don't check any condition, just we increment the s. So now we will see the structure of the chopstick is an array of semaphore which is represented as shown below. So semaphore chopstick of 5. So there's an array of chopsticks. Initially, Each element of semaphore C0, C1, C2, C3, and C4 are initialized with 1 as the chopstick are on the table and not picked up by any of the philosopher. If anyone picked, then the value of that chopstick will become 0. Now, as you can see here in
So
the code,
philosopher
as
P0 comes
and it will enter in the philosopher function. Now, while of 1, weight of takes chopstick C of I, so it will take the chopstick C0 means C0, and then weight takes chopstick of Ci plus 1 modulo 5, which means 1, so it will take chopstick 0, chopstick 1, and the value of C0 and C1 will become 0 as the weight operation. Then they eating the noodle, or we can say that eating the rice, and signal put chopstick of C, then it will put the chopstick on the table, and the value of the chopstick 0 will also become 1. And signal put chopstick of Ci plus 1 modulo 5, which means C of 1 value will also become 1. Now it will start thinking. Yeah. So as you can see here, let the value of I initial value is 0. Suppose philosopher P0 wants to eat, it will enter into the philosopher function and execute wait as I guided you. By doing this, it holds C0 chopstick and reduces semaphore C0 to 0. Now, after that, it executes wait, take off chopstick Ci plus 1 modulo 5. By doing this, it holds C1 chopstick since I0, therefore 0 plus 1 modulo 5 will become 1 and reduces semaphore C1 value to 0. So, as you can see, similarly, suppose now philosopher P1 wants to eat, it will enter into the philosopher function and execute wait take of chopstick CO5. By doing this, it will try to hold C1 chopstick, but will not be able to do that because since the value of semaphore C1 has already been set by 0 as philosopher P0 enters in there, and therefore it will enter into an infinite loop because of which philosopher P1 will not be able to pick chopstick C1. But now, whereas, if philosopher P2 wants to eat, it will enter into the philosopher function and execute wait take of check chopstick of I function. By doing this, it holds C2 chopstick and reduces semaphore C2 value to 0. Now, after that, it executes wait of takes chopstick of C I plus 1 modulo 5. By doing this, it holds C3 chopstick. Since I is equal to 2, therefore 2 plus 1 modulo 5, which is equal to 3. Now reduces semaphore value to C3. Then it holds both chopstick, which is C2 and C3. Hence, the above code is providing a solution to dining philosopher problem. A philosopher can only eat if both immediate left and right chopstick of the philosopher are available. Else, philosopher need to wait. Also, at one go, two independent philosophers can eat simultaneously. That is, philosopher P0 and P2, P1 and P3, and P2 and P4 can eat simultaneously, as all are the independent processes and they are following the above constraint of dining philosopher problem. Next, we will see drawbacks of dining philosopher problem. From the above solution of dining philosopher problem, we can figure out that no two neighboring philosopher can eat at the same point of time. The drawback of above solution is that solution can lead to deadlock condition. Now, this situation happens if all the philosophers pick their left chopstick at the same time. It will lead to the condition of deadlock and none of the philosopher can eat, and this will result in condition of starvation. As you can see here, every philosopher holds left chopstick, then it will lead to a deadlock condition. Now, possible solutions to avoid deadlock. Some of the solutions are as follows. A maximum number of philosophers on the table should not be more than 4, or we can say that we can reduce the philosopher number by 1. And in this case, chopstick C4 will be available for the philosopher P3. So P3 will start eating, and after that, he finish eating procedure, he will put down his both the chopstick, which is C3 and C4. Semaphore C3 and C4 will now be incremented to 1 by signal operation. Now, philosopher P2, which is holding chopstick C2, will also have chopstick C3 available. And similarly, he will put down his chopstick after eating and enable other philosophers to eat. Now, a philosopher at even position should pick the right chopstick and the left chopstick, while a philosopher at odd position should pick the left chopstick and then the right chopstick. This is the best solution for this problem. Now, only in case if the both the chopsticks, left and right at the same time, only the philosopher should be pick their chopstick. All the four starting philosopher P0, P1, P2, and P3 should pick the left chopstick and then the right chopstick. Whereas the last philosopher P4 should pick the right chopstick and then the left chopstick. This will force P4 to hold his right chopstick first, since the right chopstick of P4 is C0, which is already held by philosopher P0, and his value is set to 0, and that is C0 is already 0, because of which P4 will trapped into infinite loop, and chopstick C4 remains vacant. Now, hence philosopher P3 has both C3 and C4 chopstick available, therefore it will starting eating and will put down its both chopstick once finishes and let others eat, which removes the problem of deadlock. Conclusion: the design of the problem was to illustrate the challenges of avoiding deadlock. A deadlock state of a system is the state in which no progress of system is possible. Consider a proposal where each philosopher is instructed to behave as follows. As the philosopher is instructed to think till the left fork is available. When it is available, hold it. The philosopher is instructed to think till the right fork is available. When it is available, hold it. The philosopher is instructed to eat when both forks are available. Then put the right fork down first and put the left fork down next. Repeat from the beginning. So this will resolve the deadlock condition. And in the end, thank you for watching this video. And please like, share, comment, and subscribe to my channel. Thank you.